Hello and welcome to another exciting lecture by Dr. Armand. Today we'll be talking about the second half of Chapter 7 involving quantum numbers and wave-particle duality. Quantum numbers are like the electron's address for in an atom. And so that's the itinerary for today. So sit back, relax, and let the thoughts of chemistry flow in. Let's go ahead and get started. So in the part 2 of Chapter 7, we're going to be talking first about wave-particle duality. So what describes the behavior of light? Is it wave? Does it have only wave properties or does it have particle properties? And that's where we'll get into wave particle duality. And then the second component is quantum numbers. They describe where an electron is in an atom. So that's what we'll be talking about today. And so with wave particle duality, some say that particles would have wave-like natures. So in order to be wave-like, you have to have a wavelength associated with it. So a characteristic of a wave so if something has a wavelength, then it has a characteristic of a wave. And so electrons, which are particles, we had to find out a way to determine if they have a wavelength associated with it. And so it wasn't until de Broglie made a proposition that if energy is particle-like, so if energy, which is like things like X-rays, UV rays, light, IR, if energy is particle-like, and we'll talk more about that in a second, then perhaps matter is wave-like. And the reason he made this proposition is because if electrons have wave-like motion, they only allow in fixed radii, which they do according to the Bohr model. They have fixed radii. It would only have certain allowable frequencies. And so from this, he developed the de Broglie wavelength. So he took the energy of a particle, E equals mc squared, added it to the energy of a wave, and we get that for a particle, the wavelength is equal to h, which is Planck's constant, divided by the mass times the speed of the object. Because remember, if something is a particle, it has momentum. And so if you know the momentum of the particle, it's inversely related to the wavelength. So again, for electrons, which are particles, they do have characteristic wave-like properties. They do have a wavelength. So if you know the mass of an electron, which we do, and you know the speed of an electron, which we do, we can calculate the wavelength of this. Now, this only becomes important when we have very small, fast-moving particles, because something that's very large is going to have a very, very small wavelength. So for example, a baseball, which is a very massive object compared to an electron, the baseball is going to have a very, very tiny wavelength compared to the electron, which is very small and moves very fast. So again, the Broglie wavelength is only important for small, say, subatomic particles. So this showed that particles do have wave-like properties. And this was confirmed when these two scientists, Davison and Germer, showed an electron beam is diffracted by a metal crystal just like X-rays. And the reason this is important is because an electron is a particle. And X-rays, which is energy, and is wave, is made up of waves. So if the electron beam behaves the same as an X-ray beam, because again, electron beam is made up of particles, X-rays are made up of waves. It's energy, which is wave-like. So if X-rays and the electron beam behave the same, that tells you that the electron has some wave-like properties. It has a wavelength associated with it. So when you shine a beam of electrons on a metal crystal, you get a diffraction, which is like an old-timey photograph, just like X-rays. So they have similar characteristics, which helps confirm that electrons have wave-like properties. Now we want to know if photons, which are what makes up light and energy, perhaps photons have particle properties. And so if something is a particle, it's going to have a momentum associated with it. So by taking the Broglie equation and substituting in P for mass times the speed of light, because mass times velocity gives you momentum, and we rearrange this, we see that for a photon, if we know its wavelength, we can calculate its momentum. And the way this should behave is if we see a decrease in the photon's momentum, we should see an increase in its wavelength. Because again, wavelength and momentum are inversely related to one another. So as the photon is traveling, as it loses momentum, do we see a change, an increase in the wavelength emitted by that photon? And this was confirmed by an experiment by Arthur Compton, performed an experiment with a beam of X-ray photons directed at a graphite crystal. And what he observed was an increase in lambda on the reflected photons. So as the X-rays come in, say this are X-rays, here's our crystal of graphite, and then we get a resulting X-ray. So this is X-ray coming in. Oops, let me undo that. So we have an X-ray coming in. It hits the crystal. X-ray gets diffracted. When it hits the crystal, some of the momentum is transferred because it's not an elastic collision. Some of the energy gets transferred to the crystal, or the X-ray loses energy, or loses momentum. And so with the reflected crystal has an increased lambda. And so this helped confirm that photons, which are have wave characteristics, also behave as particles. So they have momentum, they must have mass associated with them. So photons have some mass associated with it because it has momentum. Again, momentum is mass times speed. So classical experiments, as we've seen, show that particle-like and wave-like properties do exist for energy. So matter, which is particle-like, and energy to be wave-like. So these are classical, a non-atomic scale. So on a non-atomic scale, matter is particle-like, it has momentum. Energy is wave-like, it has wavelength. Now on an atomic scale, it shows that electrons actually move as waves, so it has wave-like characteristics. And we've shown so that was what Divison and Germer showed, that electrons have waves. And Compton showed that photons do have momentum. And again, if something has momentum, it means it has a mass and is particle-like. So both matter and energy show both wave and particle properties. So the way we describe the behavior is called wave-particle duality because it has both energy and matter have a combination of both of these properties. And that's where the term wave-particle duality comes from. Now, one other thing to talk about, and this is getting into where is an electron. So we've been talking about how an electron behaves. It loses momentum. It has a wavelength. We want to know where is an electron. And this comes to what's called the Hesienberg uncertainty principle, which is a pretty important principle. It says it's impossible to know both the momentum and position of an electron or a particle with certainty. And with very small particles, this becomes an issue. So the uncertainty in x times the uncertainty in the momentum has to be greater than or equal to h over 4 pi. And so as you start zeroing in, the uncertainty of the position goes up. As you start getting closer and closer to where that electron is, the uncertainty in the momentum goes up so that you always retain this h over 4 pi. Likewise, if you start zeroing in on the momentum uncertainty, then the position uncertainty will go up so that this limit is maintained, h over 4 pi. And so again, for electrons, you cannot know exactly where an electron is. So it's not like the solar system where the Earth is orbiting around the sun, because we know exactly where the Earth is. For electrons, that's not true. So Bohr's model for a hydrogen atom or hydrogen-like atom does a very good job. We talked about hydrogen-like atoms in the last lecture. So that does a very good job for Bohr model. If you have a hydrogen atom or something with one electron, great job explaining. However, when you get to multi-electron species, it fails. So it can't explain, for example, how the 2 electrons in helium behave. And we also talked about, electrons behave as particles in some circumstances, but waves in the other. But neither one by themselves helps explain the behavior of electrons. So what we're going to talk about now is what's called the quantum mechanical model that helps explain how electrons behave and their location in the atom. So that's where quantum mechanical model comes in, because we don't know where the electrons are in the atom. So with the quantum mechanical model, it uses what's called the Schrodinger's equation to describe the behaviors and energies of subatomic particles. And this is a very general form of the Schrodinger's equation. H psi equals E psi. H is a Hamiltonian, E is energy. And if you have the privilege of taking physical chemistry, one of the derivations you do is deriving the Schrodinger's equation for an electron in a hydrogen atom, because it only has one electron. So we're not going to be solving Schrodinger's equation in Gen Chem 1. This is what the general form of a Schrodinger's equation looks like. And this is Schrodinger over here. Now, when you solve the Schrodinger's equation, what you get is a atomic orbital, which is referred to as a wave function of an electron in an atom. And again, these are solutions to the Schrodinger equation. And what it is, an atomic orbital is a region of electron density where you have a high probability of locating an electron. So you have like a 99.9% chance of locating an electron. So one type of atomic orbital that we see is a spherical atomic orbital. So what does that mean? It means inside this sphere, if you were to put your hand in here, you have a 99.9% chance of locating or of grabbing an electron. So it's a region. It's not an actual position. We also have atomic orbitals that look like bow ties. So inside this lobe here, if you were to stick your hand in here, you have a 99.9% chance of finding an electron. So again, atomic orbitals are regions where there's a high probability of finding an electron. And the way we describe these orbitals is by using what's called the quantum numbers of an electron. And the quantum numbers describe what type of orbital the electron is in. And we're going to be using a lot of this in chapter 8 when we talk about electron configuration. So quantum numbers in a simple term is the address of an electron. Just like you have an address. Obviously, two people who live in two different houses can't have the same address, just like two electrons can't have the same address. So remember that. So let's describe these four quantum numbers. The first one we've talked about early on in the previous lecture when we referred to Bohr's model. So again, the first one is called the principal quantum number, which is the symbol N, and it determines the overall size and energy of an orbital. It's the energy level. So the tells you how far from the nucleus you are. And so N can be any positive integer from 1 to infinity. So the higher the N value, the higher the energy level, the further from the nucleus you are. Now, if you take Gen Chem 2, sometimes in nuclear chemistry, instead of using the number N equal 1, N equal 2, N equal 3, N equal 4, which we use in Gen Chem, in nuclear chemistry, they like to use, or you may use, what's called the shells. This is the K shell, energy level 1, L shell, M shell, N shell, etc. For Gen Chem 1, we use the numbers, but don't be surprised in other areas of chemistry, they use the capital letters to describe the quantum numbers. Now, don't ask me what happens when you get to Z. You probably start back at A or something. So that tells you the energy level. So if you're thinking about this as an apartment complex, that tells you what floor your apartment is in. Next, we go to what's called the angular momentum quantum number. It's the cursive L. So again, the principal quantum number is like the floor of your apartment. What floor is it on? Angular momentum number, you can think of it as the type of apartment. So is it 1 bedroom, 2 bedroom, etc. And so notice here that L is limited by the energy level. So whatever your energy level is, L can only be a value 1 less than the energy level. And so for L, we have some common ones: L equals 0, L equal 1, L equal 2, L equal 3. Now for the angular momentum quantum number, we typically don't use the value to describe it. We use the letter. So the most common letters or quantum numbers we use are the S orbital or S shell, P orbital, D orbitals, and F orbitals. So F equals 3. L equals 3, it's an F orbital. And notice L can only be positive. So again, L can only be a positive value, and it's dictated by the value of N. So for example, for the first energy level, N equal 1, you only have one type of orbital, which is the S, because N equal 1. So we do that here. n equal 1, L can only be 0. So there's only an s orbital in the first energy level. N equal 2, L can be 0 or 1. So it can be an S or a P. N equal 3, L can be a 0, which is an S. Oops, that should be 1. A 1, that is a P, or a 2, that is a D. And so on the first energy level, we write it like this. We can have a 1s orbital. On the second energy level, we can have a 2s and a 2p. On the third energy level, we can have a 3s, a 3p, or a 3d. Note that the energy level tells you the number of types of orbitals you can have. So the first energy level only has one type of orbital, 1s. Second energy level has two types of orbitals, 2s, 2p. Excuse me. The third energy level has three types of orbitals, 3s, 3p, 3d. So the energy level tells you the number of different types of orbitals you can have. So those are the first two quantum numbers. We've got two more to do. And these are just showing you the different types of orbitals. So when L is 0, it's called an s orbital. And an s orbital is a spherical orbital. For p orbitals, which is when L equals 1, it's more like a bow tie or a dumbbell orbital. And so again, in this region, you have a 99% probability or 99 high probability of grabbing or finding an electron. Now, as the higher the L value, the more elaborate the orbitals look. So these are the d orbitals. And we'll talk about in just a second why s has one orbital, p has 3 different types of orbitals, and d has 5 different types of orbitals. And that brings us to our third quantum number, which is the magnetic quantum number, m sub L. And it specifies the orientation or position of the orbital. So again, the magnetic quantum number is defined by the L value. It goes from negative L to positive L. So if L is 0, m sub L can only be 0. So if L equals 0, m sub L can only be 0. Now if L equals 1, and this means it only has one position or orientation. L equal 1, m sub L equals negative 1, 0, 1. That's why the p orbital has 3 different types of positions. So this is 3 positions. We'll do one more, L equal 2, which is a d orbital. So since L equals 2, it goes from negative 2, negative 1, 0, 1, 2. It has 5 positions. So again, the L value dictates what the m sub L value is. Now all of these positions are what we call degenerate, meaning they have the same energy. And the last bullet is very important to remember. Each orbital can hold maximum of 2 electrons. So for example, L equals 0, m sub L equals 0. That means this can hold a maximum of 2 electrons. So the s orbital can hold a maximum of 2 electrons. Now we go to L equal 1. We said m sub L equals -1, 0, 1. It has 3 orbitals. Each one can hold 2. It has a maximum of 6 electrons. And so that's how many electrons can fill a p subshell, maximum 6. L equal 2, m sub L, as we saw, is -2, -1, 0, 1, 2. This can hold a maximum of 10 electrons. So the total, well, not 100, excuse me, 10 electrons, and that's a d orbital. So d orbitals, all of them together can hold up a maximum of 10 electrons. Now that last bullet is very important. Each orbital can hold 2 electrons. Now the last quantum number is just something for the math to work out. It's the electron spin quantum number m sub s. So each m sub L value can hold a maximum of 2 electrons. So each m sub L value can hold a maximum of 2 electrons, and they have the spin. One has plus a half spin, and the other has, and one has negative a half spin. Because if they were the same spin, we would say they would repel one another. That's why they have opposite spins. So again, each m sub L value can only hold 2 electrons. Those 2 electrons, one has a plus half spin, one has a minus half spin. So these 4 quantum numbers describe where an electron is in the atom. It tells you the energy level, the type of orbital, the number of orientations or positions, and the spin of the electron. So just to kind of give you an overview, so we look at the first 3 energy levels. So n equal 1, you have one type of orbital, L equals 0, it's called 1s. N equal 2, you also have a 2s orbital because L equals 0, and n equal 3, excuse me. And also on the second energy level, since you have an L value of 0 and 1, you also have a 2p orbital. Now for the third energy level, we have a 3s because L can be 0, a 3p, L can be 1, and a 3d, L can be 2. Now for the 1s orbital is only one type of orbital. But for the 2s and 2p, sometimes we refer to these as sublevels. And so the 1s orbital can only have one position. M sub L equals 0. So the 1s orbital can hold a maximum of 2 electrons. So each s orbital can hold 2 electrons. Maximum. So you can't put more than 2 electrons in an s orbital. Because again, it has m sub L equals 0. Now for a p orbital, it has 3 positions. So it can hold a maximum of 6 electrons. So every p orbital can hold a maximum of 6 electrons. Because each m sub L value can hold 2 electrons, so p orbital can hold 6. And then lastly, the d orbital, which has 5 m sub L values, can hold a maximum of 10 electrons. Now for the first energy level, n equal 1 can hold maximum 2 electrons. N equal 2 can hold a maximum of 8 electrons. N equal 3 can hold a maximum of 18 electrons. And there's a general rule to use. Max number of electrons in an energy level is equal to 2n squared. So if you square the principal quantum number multiplied by 2, that'll tell you the maximum number of electrons in an energy level. Now remember, each m sub L value has each electron in the m sub L value has first a plus a half and minus a half spin. And so sometimes the way we talk about these electrons is drawing something what's called an electron orbital diagram. We actually show the actual electrons in the orbital. So again, for the 3s subshell, 3 represents the energy level. The 1 dash here represents the L and M sub L values. And then the 2 arrows, one pointing up and one pointing down, represents the M sub S values. So for the 3p, again, N is represented by the 3. It's a p orbital because L equals 1, and there's 3 M sub L values. That's why we have 3 dashes here. And each one can contain 2 electrons, one with a plus half, one with a minus half spin. Now for the D subshell, we have M sub L of 5 values. That's why you have 5 dashes in that subshell. And each dash can hold 2 electrons. So this is a way that we'll use in chapter 8 when we talk about electron configuration and orbital diagrams. This is how we're going to draw the orbital diagrams for elements and ions. So this is an overview of the 4 energy levels. So for the first energy level, L can only be 0, M sub L can only be 0. It's the 1s subshell, has 2 electrons. So here we do the equation that I showed you, 2 times n squared gives you that. And it goes through and you see the greater the energy level, the more electrons fit in those energy levels. So the larger the energy level, the more electrons you have. So make sure you remember how to calculate the L and M sub L values from the N value. Let's look at an example. Say we have N equal 1, L equals 0. Let's do something else. We've done these. Let's say N equal 5. L is going to equal what? It's going to be 0 to 4. So notice that L is always, the maximum L is always 1 less than the N value. So L equals 0, which is an s orbital. M sub L equals 0. We also have for the 5th, we have L equal 1, which is a p orbital. M sub L equals -1, 0, 1. Then we have L equal 2, which is a d orbital. M sub L equals -2, -1, 0, 1, 2. Then we have L equal 3, which is an f orbital. M sub L equals -3, -2, -1, 0, 1, 1, 2. And then lastly, we have L equal 4. You may not know this one. This is called a g orbital. So notice the higher the L value, the more electrons you can put in it. This is -4, -3, -2, -1, 1, 2, 3, 4. And I forgot to put a 3 here. So in the first, the 5s, this is called the 5s subshell. This is the 5p. 5d, 5f, and 5g. Just to let you know, currently no element has electrons to occupy the 5g orbital. And so the maximum number of electrons, we have 2 in the s, 6 in the p, 10 in the d, 14 in the f, and 18 in the g. That's a total of 50 electrons in the n equal 5, the fifth energy electron orbital, energy level. Give you a few seconds to look at that. All right. So now let's look at this question. Which quantum number describes the shape of the orbitals? So again, n sub s tells you the spin of the electron, which is either plus a half or minus a half. So this can't be that one. L identifies the shape. N identifies energy level. And M sub L, I spelled that wrong. Jeez, let's see. N identifies, well, that's right, energy level. M sub L describes the number of positions. And so the correct answer is L, which describes the shape of the orbital. The following are bogus. So S is a type of orbital, M is a type of energy level. So this is a good question. Here it wants us to identify which of the following is an invalid set of quantum numbers. So we look at the first one, n equal 2. So n equal 2, L can be 0, M sub L can be 0, M sub S can be a half. That's a good one. So it's not A. B, n equal 3, L equal -1, M sub L equal 1, M sub S minus a half. Now here we have a problem. L cannot be negative. It can only be positive. So B is one of the ones with an invalid set of quantum numbers. L cannot be negative. Next we go to number 4. N is 4, L is 2, that's fine. M sub L is 2, M sub S plus a half. Nothing wrong with that one. D, N equals 3, L equals 2, that's fine. M sub L equals -1, no problem. M sub S plus a half, not an issue. N equals 4, L equals 3, that's legal. M sub L equals 3, no problem. M sub S plus a half, not an issue. N equals 5, L equals 4, okay. M sub L equals -5, M sub S minus half. Now we have an issue, because if L is 4, M sub L cannot be -5. So that's one of the invalid quantum numbers. So again, M sub L can only be from -L, 0, positive L. And since M sub L is 4, it can only go from -4, -3, -2, -1, 0, 1, 2, 3, 4. So as you see, -5 is not a valid M sub L answer. So those are the two correct, those are the choices with the invalid quantum numbers. So here we want to write the three quantum numbers. So disregard the electron spin of the electron in a 4D orbital. So we have a 4D orbital. We want to write the three quantum numbers for this. So again, we're looking at the 4D. So just from this name, we can get two of the quantum numbers. So the 4 represents the energy level. So N equals 4. The D represents the type of orbital. So D is L equal 2. And since it just says the 4D orbital, M sub L can be anywhere from -2, -1, 0, 1, 2. So again, the 4 came from the 4 in the 4D orbital. That tells us the energy level. The L equal 2 came from the D in the 4D description. So D is the L equal 2 value. And then since L is 2, M sub L can be -2 to 2. So here we want to know how many electrons occupy the fourth energy level. For some reason I put 3, but we want to know how many electrons occupies the fourth. So here N equals 4. So N equals 4. Let's see now. N equals 4. L equals 0. L equals 1. L equals 2. L equals 3. So M sub L equals 0 for the first one. For the L equals 1, M sub L equals -1, 0, 1. Oops. For the second one, M sub L is -2 to 2. And for the third one, M sub L equals -3, -2, -1, 0. Now you could have used the equation I provided for you early on, that the maximum number of electrons is 2n squared, but I want to show you with this how it's done. So the s orbital can hold 2, the L orbital can hold 6, D orbital 10, and the F orbital 14. So that's a total of max electrons equals 32. The second question wants to know, if L is 3, how many electrons can occupy that subshell? So if L equals 3, M sub L equals -3, -2, -1, 0, 1, 2, and 3. And remember, each M sub L value can hold 2 electrons. So the maximum number of electrons here is, that's right, 14 electrons in the L equals 3 subshell. So make sure you know the rules for these quantum numbers, because the next lecture will be covering electron configuration. And you got to know that what each quantum number means to help describe where an electron is in an atom. So that's it for today's lecture over quantum numbers and wave particle duality. I hope you enjoyed the show. If you did, make sure to press the like button, or if you'd like to leave comments, always appreciated. That's it for now. Until next time, have a good rest of the day or evening whenever you're watching this video.